Hi, everyone. My name is Johannes. I am a PhD student in Bochum and currently pursuing a PhD in homomorphic encryption. And one of my latest projects, together with my supervisor, Tim Gunesu, was about key switching in BGV-like schemes, which I'm going to talk about today. And what I want to do today is take you into key switching in all the nitty-gritty details. So we will try to answer 3 questions today. The first one is, what even is this key switching thingy that I'm talking about here? Then why should I care about improving it, or why should you care? And how can we actually improve it, right? So my goal is to answer these 3 questions. If I'm missing anything or something, feel free to ask questions in the chat. So yeah, then I can help out, hopefully. So this is me. I do crypto research, as I said. I like football. I really like coffee. It's a great thing. And I also love food. And the thing about homomorphic encryption is that it can sometimes be a bit overwhelming with all the math details and so on. And so I thought of an alternative title to today's talk, why repackaging food is really annoying and how to improve it. And so we're just going to start talking about food because I love it, you know. Let's say you have a great idea, right, for a recipe, for example, for a stew pot. You have this amazing idea, but you are also really lazy and you don't want to cook it. So lucky for you, I have good news. We have a new hotshot in town, a company called Food Hot and Easy, where you can send them your ingredients and the recipe, and then you just receive your food and it's hot and easy, right? It's like a great service, can recommend. So how does this look like when you do this? Well, you take your ingredients. For example, you have eggs and onions that you want to add there. You send it to this company. They have a machine, a peeling machine, for example, that removes that. And you also have some stuff like potatoes or broccoli. And then all of this is together put into another machine that cooks your food, and out you get your dish. Now, you might say, this is all great and dandy, but this is my grandma's recipe. I can't tell everyone what I'm using, right? The good thing is this company offers a second service, which is you pack up all your ingredients into a package, so they don't know what they receive anymore. And they have these machines where you can just put in a package, it will be processed, and then another package comes out. And in the end, they will send you the package back, and they never saw what was inside. Now, obviously, I'm not only talking about food here. Most of you are familiar enough with homomorphic encryption that this is supposed to be an equivalent to homomorphic encryption. And I'm simply cooking up some metaphors, namely, our food is our data, our packets are ciphertexts where we encrypt them in, and we have the operations that we want to perform on our data. These are our little cooking machines. And then we have these weird machines to perform our operations on the ciphertext. And to understand how we can use this or how this works, we will look at the individual steps on how this works. So the first question is, how do we actually pack up an ingredient, or the homomorphic world, it would be how do we encrypt something. Now, for BGV-like schemes, we're usually working with the ring learning with arrows problem, which is math over the ring RQ. And basically, in the ring RQ, we have polynomials with n coefficients, where n is the polynomial degree. And we're having a ciphertext modulus q. And so each coefficient in this modulus is in this polynomial is mod q. And what you can think of, what happens if we do an encryption is we take our package, which is mathematically it's some random element, and our secret instruction assemblies, and then we add our content. In this case, for example, the broccoli, and we also add some water, which acts as a distraction. So if you lift up the package because of the water, you don't really know what's in there, right? And then what you're going to do is you say, look, I constructed this package from this material. and this is my final package, but I'm not going to tell you more about it. And we will assume that this is secure, right? There's some clever mathematicians who take care of this, but for us, it's enough to assume that this is secure. And so, okay, this is how we pack up an ingredient. How do we recover the food from such a package? Well, we take the material again, we take the package, and now we take our instructions, our secret instructions, and with these we can open the package and recover our food, but with the water, right? And so if we, metaphorically speaking, if we put it through a sieve and remove this water, then we can recover our message, right? And one perspective mathematically that is very helpful is to think of such a ciphertext as a polynomial in the secret key S. So if you evaluate this polynomial in S with C0 plus C1 times S, you get out M plus E, which is your message with the error, but okay, this is kind of like everyone could remove the error, so you already decrypted it. And we're going to use this representation to understand quite a few things about what's going on for FHE operations. So, all right, we have two packets. Now we want to cook something up. What do we do? Well, if we have two ciphertexts, C and C prime, and we want to add them, for example, or add the underlying data, what we do is we simply add the parts, right? We calculate C0 plus C0 prime and C1 plus C1 prime, and everything is fine and good. Now, there are obviously other things we might want to do. For example, multiplication, right? We again have two polynomials, but if we multiply them, we actually get out a three-part ciphertext. So it doesn't really look like a package anymore, but we get more something like a can out of it. And the problem with our can is that we really don't want to combine a package and a can. This gets ugly really fast. And this is basically what we're trying to resolve in key switching, right? So we get this weird looking can out instead of our package that we expected with three parts, C0, C1, and C2. And we want to transform this back into a package that we know how to handle. And so we have a C0 and a C1. We can leave them as they are, in fact, because we know how to deal with that. But we have this weird term C2 where we require this squared secret key suddenly to unpack our food. And so the whole idea of key switching is to take this single term and transform it into a package, but with some additional error. So we get out a C0 plus C0 tilde and a C1 plus C1 tilde as our package, which we can use for decryption. Now, to do so, we need a special ingredient. And the special ingredient is, in this case, our secret key squared, or our instruction squared. Because we need to change the packaging, we also need to know how it was made up. And so what we basically do is we do an encryption of this secret key, right? Which we consider to be a special kind of package. In this case, it's a green package, but we can still assume that this is secure under our ring learning with errors assumption. And so we build up this special package, which we then use as our so-called key switching key. And as a normal ciphertext, our key switching key also has two parts, right? And we can also consider this kind of as a polynomial in S. So what happens if we use our secret key, our special ingredient, sorry. So let's combine it with our C2 from our previous example and just multiply C2 to both parts, evaluate it in the secret key, and let's see what happens, right? So we're combining our can with our special ingredient. Now, if you just plug in the stuff that we defined, what we get out is actually super nice. So we get out C2 times S squared, which is great. This is exactly what we wanted to compute. But we only used the key switching key, which we can publish because of our security assumption, and only C2. So no material in that sense. The other part we get is though C2 times C. So are we done? Sadly, the answer is no, because this basically destroys our whole package, right? We have this error, and since we multiply it with an element from RQ, this is just way too big. It just basically floods our whole package, destroys our content. We don't have a fancy meal to eat afterward anymore. Not going to work out. What can we do? Well, that's a good question. One thing we can do is we can plug this leak with a modulus extension. So we have to, the idea is that instead of doing this key switching over our ring RQ, we go to a bigger ring, RQP. And the only modification we have to make is add this little factor P in our key switching key, right? And when we now plug this in and use it and divide it by P in the end, something really cool happens. So you see the modifications are highlighted in green. It's not a lot, but since we added this P to our key switching key, it will cancel out with the division by P that we do. But for the error term, it will still be divided by P. And so suddenly we're reducing our error only with a slight modification, right? And so obviously we have to choose P in a way that makes sense, but this already solves our problem of getting a package. Now, this is actually the second variant that we know how to control the error. There was an earlier variant, and a variant that was discovered earlier. And it's something that is quite common in lattice cryptography, which is decomposition. So the idea here is that you take your can and you decompose it into smaller cans. So let's say, for example, into 4 cans. And now you're working over 4 elements, but in a smaller ring or in a ring where the coefficients are smaller over R beta. And the idea is that you decompose it in a way that when you add different, if you add the different parts and scale them correctly, that you get back your original ciphertext. And for the key switching key, we also now need 4 versions of this, right? So if we look at the part that is not just the random element A, but the interesting part, we get out these 4 variants where we exactly add our reconstruction mechanism, if you want, for the ciphertext to the secret key parts. And what happens now if we use that one is, well, okay, we first decompose the ciphertext. Our multiplication that we did before now is a dot product, but it's still kind of a multiplication in that sense. And what happens is that we just perform the dot product. We reconstruct, by unpacking all of this, we reconstruct our C2 times S2. And now we have, instead of C2 times E, we have the sum of all of these, the number of decompositions. So in this example, it would be 4. But we only multiply each individual error, which is small, by an element from the ring with coefficients in beta. And so this is basically the second method to reduce our error that we know in key switching. And well, we can put these together, right? We're not limited to one. They're not exclusive or something. So we can put them together. Now we put the P also in front of our secret key squared. And if we now use our can, we first decompose it. We then combine it with our really big special ingredient. Then we get out our package that we wanted all along, so we can continue computing. And what this looks like is this. So you can still see kind of that the original structure is there, right? But now we simply add the decomposition and we divide by the bigger modulus P, or by this extension modulus, to combine both methods of error control. And now the only challenge remaining basically is, how do we actually choose these parameters in a way that this works out to some noise that we can really handle, right? But these are the fundamental ideas, and we will talk about the parameters a bit later. So let's see. Maybe it's a good time if we have a couple of... Nope, we don't have questions. Great. then I will continue. So this is about the first question. What even is this key switching thingy? Okay, we have a question. Is key switching only applied for C2? Yes and no. So C2 is an example in this case. There's also another case where we will apply it, which is rotations, right? So we will rotate when we rotate the underlying data, then we also modify the secret key, and we can also use it for that. And then maybe a quick question for this: are they decomposed items of equal size? Usually they are. All right. Cool. So let's continue and try to find out why we would even want to improve key switching. Well, the first thing is that we need it after every multiplication, or we need it after every rotation, as I just said. And so we need it quite often. Now, there are some exceptions and some optimizations we can do for that, but at some point we don't get around using key switching. And the second problem is, so it appears often, and then it is really slow. And to see that in action, I brought 3 questions. Some of you are more familiar with bootstrapping or with homomorphic encryption, know about bootstrapping. Maybe they also seen 1 or 2 use cases. So I just want you to take a moment and think about answers to these questions for yourself. What do you think? How large is the percentage of key switching in bootstrapping? How large in the matrix multiplication and a homomorphic one? And how much slower is it compared to a ciphertext multiplication? Well, it's a lot, is the short answer. The longer answer is, for example, in bootstrapping, it's roughly responsible for 40% of the execution time. In a homomorphic matrix multiplication, it's more than 50%. And when you compare it to a ciphertext multiplication, it's 11 times slower. So we're talking like really slow here. And basically what we want to know is, why is it so slow, right? Because before we can improve it, we need to understand where is this coming from. And to understand that, we have to look at how do we actually implement homomorphic encryption. And there are 2 techniques we use for this. The first one is relevant to multiplication. So if we want to multiply 2 packages, let's say, the naive approach would take time n squared, and we would get out another package. But we have this nice thing called the number theoretic transform, where we basically decompose our large package into many, many small packages. And then we can multiply in time O of n, and then we take this package and turn it back. And if you just walk down the path at the bottom, you will have an overall complexity of n log n. And this speeds it up. It doesn't mean it's cheap, right? This is still one of the most expensive parts, but this is what we do to speed up at least the multiplication over our ring RQ. We can obviously do the same thing for cans, just to make this clear, right? We can also do a can theoretic transform. And the other part that we use is that we use a residue number system. So this is really similar to the decomposition idea, right? So you take the ring RQ, but you divide it into smaller chunks, RQ0 to RQ5, for example. And then instead of computing on the large thing, you compute on the smaller things. And this is a good thing in general, because, for example, we could decompose it into chunks of 64-bit, which our computer just can nicely handle. But it also has some drawbacks. The first one is we lose some operations, right? Which is we cannot divide and we cannot do modular reduction anymore that easily. And the second thing is that we need to perform entities on or number theoretic transforms on all of these elements separately. And then in order to interact, we have to go back to our normal package, to our coefficient domain, how we often call it. And the second thing, so these are the 2 basics we use. And there's another thing that actually makes key switching slow or homomorphic encryption in general, which is large parameters, right? And so how do we actually choose these parameters to control our error? Well, in the end, it's pretty simple. We want to choose P roughly as large as our largest decomposition, which is also why we're trying to decompose into items of roughly equal size. So if we don't decompose at all, right? So if we take all 6 elements as just one, then we have to set P roughly as large as all of these elements together, which is basically the whole ciphertext modulus. And I mean, we're already talking about the ciphertext modulus. This might be a couple of hundreds, maybe 1,000 bits. And so this would be really, really tough. But you can also see that if we increase the number of decompositions, we can reduce the size of P, right? And so if we go to the other extreme where we say, all right, we decompose really into all the individual parts, then we will only have to choose P the size of one of these moduli, Qi. And the other part that makes it, so this is one part, we already deal with large parameters, right? The other part is that it takes a lot of steps using our more efficient representation. So it's the best we know, but it still takes a lot of steps to compute a key switching. And we will just go through that step by step for now. So the first thing you do is you start out with your decomposition, right? You have your C2 again as our example. And you have this, let's say we divide it into 2 groups, into the one group Q0 and Q1. And then the second group is Q2 and Q3. So the first thing that you have to do is, when you receive that, is, oh, wrong direction, you have to extend this to the whole space, to the bigger space that you want to work on, so Q times P. You have to do this for both elements, and actually you need also to combine all of these elements, so this has to happen in the coefficient domain. And yeah, so this is the first step. Then we take this from the coefficient domain, and we go to the entity domain, so to our fast multiplication representation with a lot of small cans. This is now for the rest of the slide. This will be in green. And this is the first expensive step we have to do. And now comes a really annoying part as well. So now we take this, we read our key switching key from memory, we perform the dot product that we have to do, and then we get something out that this looks like a package again, luckily, but is still in the fast multiplication representation. And the issue here is that these key switching keys can become really, really large, and basically we're reading them for one-time use, and afterwards don't need them really anymore until the next key switching. And so reading from memory, in addition to performing these forward and backward transforms, is the second part that makes key switching really, really slow. And speaking of transforms, now we have to take this output, transform it back to our normal domain again. And now we also need additionally, I told you we can't do divisions anymore. So now what we need to do is we take our CIs that are mod P0 and P1. We need to convert them to something which is a delta I to make sure that our ciphertext is divisible by P, because then one of the things we can do is we can multiply with the multiplicative inverse instead of dividing, and this corresponds to the same thing as long as this is divisible. So we're computing this delta I to make sure that this is a correct operation, and then finally, when we add all of this up and multiply with P to the -1, we get out the output that we need. And as you can see, this involves quite a lot of steps, forward, backward transforms, and is really, really expensive. And now the question is, okay, this is expensive, but how can we improve it actually, right? What do we have to do? And basically what we looked at in the paper is quite a few things, but to understand where we are coming from, it's maybe a good idea to look at the 2 most relevant recent works. So there are more papers that we also reference in our paper, but I think these serve as a great foundation. The first is by Kim, Polyakov, and Zucker, where in their extended version on the IACR ePrint, they define all of these variants, and they define also how many operations you need, but they don't go a step further, and they don't do a computational analysis. Sorry, they do a computational analysis, but no complexity analysis or look at what the best parameters are. And then there's a work which was published last year at Crypto, where Kim, Lee, Seo, and Sung, they looked at how a new technique for key switching, the double decomposition technique. And what they did is also, they did a complexity analysis of key switching, but they took slightly wrong turns in there, which we're going to look at. And so this led to wrong conclusions also about their technique. And so what we did in our paper is we took another perspective on key switching, right? Using that, we provide some simple guidelines for optimal key switching parameters. We also introduced and revisited a couple of ideas for better parameters. We reduced the number of multiplications in key switching, and we also provided an improved analysis for the double decomposition technique, and also an improved comparison. And so I will talk about the first 2 points and the last point. The other contributions are obviously in the paper if you're interested. But I will for the sake of time, I will only talk about these 3 things. So what is this old perspective we wanted to improve upon? So the old perspective basically was, okay, this is the number of entity operations we have to perform in key switching, right? We have this omega, which is the number of decompositions plus 2, and then we have the number of primes in Q and the number of primes in P. And basically in their paper, what the argument is, okay, so for security reasons, we kind of have to choose K in O of 1, and then omega follows as O of L, as we saw on the slide of choosing parameters. And then just if you plug this in, you get a complexity of the number of primes in Q squared. And the approach we took is to say, well, this is not quite true. So because you're implicitly limiting your parameter space. And what you actually have to do is you have to consider omega as a parameter in the security level. And then you also have to factor in the complexity of the entity itself, right? Of the number theoretic transfer. And so what we actually then said is, look, you can choose omega anywhere between 1 and L, and then you have to choose maybe your degree accordingly to keep it secure. But then you get out K is from L over omega, so you have a bigger space to choose K from. And then you get this complexity omega L n log n. And if you can still assume, okay, and maybe I don't want to increase my degree or anything, then you have a lower bound maybe on omega, but you can still choose it in a more flexible range than previously was claimed. And so if you fix the degree, I like this bound a little bit more, then it's omega L, and basically it reads like a little cute owl. So I really like this. I always had to think of that. But the real bound that kind of is interesting is to consider it as another parameter in the security level and give you a bit more freedom in choosing it. And so when you do this and you analyze all of this, which we do in the paper, then you get a really simple, you get really simple guidelines for choosing key switching parameters. So first you calculate how large Q must be, right? Which is something that depends on your use case. Then you calculate how small n can be. So you're trying to choose the smallest degree while still staying secure. And then what you do is you choose your omega greater or equal to as small as possible. Now, why not 1? The answer to that is in the number of multiplications. So the more multiplications you have, or wrong, the number of multiplications, the optimal complexity for this is the square root of the number of primes in Q, so the square root of L. And often omega 2 is closer to that, and because of that, you get the same or even better performance. And what do I mean by as small as possible? Well, now obviously, since you fix your degree n, if you fix your degree n as small as possible, then you only have a certain space left for your modulus p, or you can also use the remaining space to figure out how large really omega can be, and then you choose these parameters together, so to speak. But the simple guideline you can remember is choose omega as small as possible, right? And so we use this to also take a look again at the double decomposition technique. And the double decomposition technique is actually really, really cool idea, right? So you have the same process as before. You have your cans in the beginning, and then you decompose this into your smaller elements. You extend this to the big modulus, what we talked about, and then you do a second decomposition to another common base RE, in which you perform the dot product. And basically, the observations they made is for certain parameters or in certain configurations, you can you can have less primes for this basis E than you need for Q times P. And then you need less entities and you can be faster. It turns out that in practice, things don't quite work that way. So the first problem is that for the computational optimum, you need to choose omega equal to L. But this is completely contradictory to the memory optimum, which requires omega to be 1. And so you have this fight of the two things that make key switching slow: the computations of the entity and also reading the key switching key from memory. And because of this, it is really hard to come up with optimal parameters for this technique. And this can also be seen when you then choose these pairs. So we chose in our comparison, what we did is we kept it a bit more simple, and we said, okay, look, we choose the parameters optimal for each approach. And this is different to the original comparison where they used the same parameters for each approach. So they didn't look at the approaches individually and thought, okay, what's the best parameter we can choose? But they used the same parameter set to compare these techniques. But if you choose them optimally and you evaluate this, you get out a slightly different picture, right? The first one is, so what we did is basically we fixed the degree and we looked at, okay, given your use case uses maybe 50 or 70 or 90% of the available modulus space, how well we choose the key switching parameters optimally with respect to the computational complexity, and how well does it perform. And as you can see, the green line, which is the double decomposition technique, is way above the single decomposition technique, with one exception, that is for 95% with degree 2 to the 16. But it turns out actually we have a couple of more parameter sets in the paper. This is the only time the double decomposition technique outperforms the single decomposition technique if you choose parameters for computational complexity. And the other issue is, what I mentioned is when you do this, you have even larger key switching keys. So it turns out that while the technique is super cool and it is a super interesting theoretical advancement, which we had in key switching for a long time, for implementations and for real parameter sets, it didn't turn out to be as helpful as initially thought. All right, so this is the end. I hope I could answer all three questions for you. If you have any more, feel free to ask them now. Also, this is the link to our paper where you can have a look at what exactly we did and all the math behind it, and also the other ideas on reducing key switching parameters. And I'm happy to take questions, I suppose.